Hello. We're going to consider a special circuit where you basically have a battery connected in series with a resistor and a capacitor. The resistance will be R, the capacitance will be C, and then they're connected with a switch. So the battle plan here is to try to figure out how this circuit's going to behave over time. So let me explain physically what's going to go on. So if you look at this battery, it has a voltage V sub B, maybe it's 12 volts or something like that. And instantly when the switch is open, it notices, oh, wow, there's all this over here that has a voltage of 0, and I've got a voltage of, VB. So I'm going to start pumping positive charges out this way. Again, we're dealing with conventional current, not reality, which negative charges would be going the other way. But we're going to just pretend like it's positive charges. So what's going to happen is these positive charges, compelled by a decrease in voltage across the circuit, is going to send positive charges around through the resistor and then onto this plate. Well, that's an open circuit, so current can't actually jump across there. But what can happen is when a positive charge gets here, it's going to compel a positive charge over here to run away, because like charges repel one another. So that's going to force a positive charge here to go through this closed switch, remember, which means the line will be straight. So it goes all the way around here and comes back. And it keeps doing that until basically there's a voltage difference between this plate and this plate that equals VB, the voltage of the battery. So these positive charges are going to continue to compel positive charges to leave here. So it's just like current goes. But once this voltage across here happens to match VB, all that's going to stop, and it's just going to be basically a charged capacitor. That's, of course, when they're a little dangerous, because you might grab one and get shocked a little bit. So let's work out the mathematics of how this plays out. So with this circuit, we need to know a few things. One, we need to recall that capacitance is equal to charge per unit voltage. So that allows us to figure out what the voltage drop across capacitor will be. We need to know Ohm's law, V equals R. That allows us to determine the voltage drop across the resistance. And we need to remember that I, the current, is equal to dq dt. Once we have those, we're good to go. We're going to apply Kirchhoffs loop rule, and we're going to start here and go all the way around the circuit, assuming we just close the switch. So what we get is VB. That's the increase in voltage in going from this negative side to that positive side. And now I'm going in the direction of the current I, which is a function of t. So I'll just write it I of t over there. Let's get this focused a little better. Okay, and I'll try to write bigger too. So this current going through this resistor is going to cause a voltage drop, and that voltage drop will be, since we're going the direction of current, it's a voltage drop, it'll be I times R. And then when we get over here, the voltage across this at any one time is going to be the charge across it divided by the capacitance. And again, that's going to be a voltage drop, so I'll say minus the charge on the capacitor, and that's technically a function of time as well, over C. And now we're back to where we started from. So according to Kirchhoff's loop rule, that's equal to 0. So what we're going to do now is try to solve this and try to get it into a form where we can actually solve a differential equation. Using I is equal to dq dt, we can get everything in terms of the Q, which is a function of time. Of course, the voltage is going to be a function of time, the voltage across capacitor, that is. The voltage across the resistor as well. And the current is going to be a function of time, and the charge on the capacitor is going to be a function of time. So we're going to work all that out. So I'll put in VB, and I'll pull these over here just to get rid of the negative, because I'm bound to drop them by accident if I don't. So I'm going to say that's equal to R times dq dt. And then the Q is just going to be plus 1 over C times Q. So we sort of have a differential equation at this point. I can make it a little more straightforward by multiplying both sides of the equation by C. And you'll see why later. I just happen to know what the results are going to be, so it makes my life a little easier if I do this. So I'm going to say now I have C times the voltage of the battery is equal to R times C times dq dt plus just plain Q, because that C is going to cancel out the C down there. So I want to get basically all, this is a separable differential equation, so I'm trying to get basically this dq with the q, because the q is going to be a function of time. We can solve for the q. Then we can realize that the voltage across the capacitor is given by q over c, and we can realize that the current is, which is also a function of time, is dq dt. So if we can solve for q of t, we'll be good to go. So what I'm going to do is I'm going to pull this q over to the other side. I'll get c vb minus q, and I'll go ahead and put it up time just so we can fit our hold our mind in such a way that we can make sense of this. So we're now going to treat these q's as functions of time, and on the other side we're going to have just plain RC times dq, again as a function of time, over dt. At this point, I can see that if I divide both sides by CVB minus Q of t, and then divide both sides by RC and multiply by dt, then I get a separable differential equation that is really nice. So I'm going to drop the of t stuff, since y'all now probably have a good understanding that these Q's and V's and I's are functions of time. So I'm just going to write dq over CVB minus Q. Okay, that's what happened when I divided through by CV minus Q. And then on the other side, when I multiplied through by dt and divided by RC, I got dt over RC. Okay. There's no real reason to do this, except I know what's going to happen. When I go to integrate this, I'm going to have to deal with the negative in front of the q. So I'm just going to multiply through by -1 on both sides just to make this a little more straightforward. So I'm going to say dq over q minus cv is equal to negative dt over RC. Again, this is just a trick I'm doing to keep my integral to be a little less complicated. So now I'm going to integrate this from q equals 0 to q of t, and I'm going to integrate this negative dt over RC from t equals 0 to t. When I do that, I can say, oh, well, I could just make a straight substitution, let u equal q minus cv. And when I do u equals q minus cv, then dq is just du. That's why I got rid of the negative. So I just have a dq over u, and then the integral of that, of course, is the natural log of u. And on this side, I'm just going to get t, negative t times over RC. So I now get ln, the natural log, of q minus cv evaluated from 0 to q of t is equal to negative t over RC. So I need to take the ranges of integration into account. In so doing, I'm going to get the natural log of q minus cv, and that's q of t now. So I can put that there if I like. Over, when q is 0, I'm just going to get negative cv. So I've got that equals negative t over RC. To get rid of that unsightly negative, I'm going to flip the order back around, but I've already, saved myself the problem of substitution with a negative, so that's fine with me. And I'm going to raise both sides, or raise e to the left-hand side power and raise the right-hand side, or e to the right-hand side power, and set them equal. That's the way we pretend it's going on. It's a little more complicated mathematically, but this is essentially what we're doing. So that allows us to solve the system, or solve the equation. So when I take the the raised to the e power, the ln of something, then all I get is the argument. So what I now have is q of t minus cv over, oops, I forgot to do that opposite order. So minus cv, I'll change that in a second, is equal to e to the negative t over RC. Now that RC is actually a symbol we call tau, and it's just the time constant for an RC circuit. If you actually multiply ohms times farads, you can make out that the actual RC has units of time, so that's kind of neat. But I'll just stick to RC for right now. So now if I want to get rid of that negative CV, all I have to do is, no, I'll go ahead and keep it, it's fine. So I'll say Q of T minus CV is equal to negative CV e to the negative t over RC. Or pulling the CV over to the other side and factoring it out, I'll say Q of t, Q is a function of time, is actually equal to C times V times, when this comes over there, that'll be positive, so it'll be 1 for that one, minus e to the negative t over RC. So that's the actual charge as a function of time. Basically, at t equals 0, this becomes e to the 0, and e to the 0, of course, is 1, so 1 minus 1 is 0. So it's basically an exponential growth curve that looks like this. And it's asymptotically approaching c times v over time. So this is the Q as a function of time, and this is the time. That's our actual graph, roughly what it should look like. So it should exponentially grow. So that gives us Q as a function of time, which is pretty helpful. I can now calculate the voltage across the capacitor by realizing that the voltage is Q over C. So V of t would just equal Q of t over C, which means I'm just going to get rid of that little c, and I get V of t is actually equal to V sub B. I've been dropping this B, that's kind of bad. Let me put it back in because, you know, I'm a goober. So there's the B's that I've been dropping. Oh, drop one over there too. Man, helps to have students so they catch me from making these boo-boos. Anyway, so that's VB times 1 minus e to the negative t over RC. So what we see is, yeah, the voltage across the capacitor is going to grow just like the charge leaving the actual battery. It's going to grow, but it's going to asymptotically approach, in this case, a voltage VB. So it's the same curve, except we're putting voltage on the vertical axis, and this asymptote is V sub B. Now, the last thing we need to calculate is the current, I, which is equal to dQ over dt. That's easy enough. Let me move this paper so you can actually see it. Actually, let me move the camera so you can see the paper. That might be a little easier. There you go. So I is equal to dQ dt. So what I'm going to do is say I of t is equal to d by dt, and I'm going to actually distribute it so it makes it a little easier. I'm going to distribute the CVB. So I'll say CVB minus CVB e to the negative t over RC. Okay, that way you can immediately see, oh, this is just a constant, so that one's going to give me nothing. But that gives me a negative out front and a CVB because those are just constants. Now the integral, or excuse me, the derivative of the exponential is just the exponential, and then I got to take the derivative of the actual exponent. So it'd be e to the negative t over RC times the derivative of the exponent, which would be negative 1 over RC. So you see this negative and this negative is going to cancel out. This C and this C is going to cancel out. So I'm just going to get VB over R out in front. And finally, I have I of T is equal to VB over R times E to the negative T over RC. Now, this is an exponential decay curve. And what that means is initially the current is a maximum value of, so this is the current right here, I, has a maximum value of VB over R. In other words, the circuit doesn't even know anything about the capacitor. It just thinks, oh, there's a resistor over there. I'm going to start putting out some current consistent with Ohm's law. But then over time, it's going to fall, and approach 0. So the current will actually go to 0 at the same time that the voltage across the capacitor goes to VB. So that's pretty much how the circuit's going to behave. You can see RC basically, if you let t equal 0, then you're going to get there, and you're going to get here for the current, and here for the, or excuse me, here for the voltage, and here for the charge. They're all going to be 0. But if you allow one time RC to pass, if you look here, this RC and this RC is going to be e to the negative 1, which would be 1 over e, so it'd be 1 minus 1 over e. times CV. So basically we're changing by 1 over e to the 1 each time constant. In this case, we're actually changing by e to the negative 1 each time constant, each RC. So that 1 over e and e to the negative 1 are basically are two parameters that can give you some idea of roughly what percentage the current or the voltage or even the charge changes by. So that's sort of what some of the examples are about. But the main thing is you need to know that this is the charge per unit time across a capacitor connected in an RC circuit like the one we've shown. This is the voltage across the capacitor as a function of time, and this is the current going or leaving the battery, if you will, as a function of time for this type of circuit. That's it.